Alrighty, gang. Sorry, I'm running a few minutes behind. I got a little caught up in office hours. Ugh. Welcome back to Calc 1. We are very near the end. Not a whole lot more left to do in the course. In theory, you are now proficient with U sub, both in indefinite and definite integrals. We've gotten lots and lots of practice with that over the last 2 lectures. Today, what I want to do is introduce the concepts that we're going to be playing with a little bit next week. So next week, we're going to do just a few things. Well, really just one thing as far as content is concerned, and that is talking about section 6.1, which is on areas between curves. That, of course, is going to relate to definite integrals because, you know, definite integrals measure areas under curves. So let's do it. We'll have occasion here to use some U sub. Let me throw the title card out real quick. This is MAC 2301, section 004, which is a Calc 1 class. And the date today is the 15th of April, 2022. The game today is to polish our U sub skills and introduce areas between curves. So I have a funny story behind this that I like to tell. When I was taking pre-calculus, MAC2311.004 back at the community college in the town where I'm from, we were learning how to graph polynomials, and my professor, you know, we finished this problem. We were sketching 2 cubic polynomials or something like that, and one of them looked, you know, something like this, and maybe the other was, maybe it wasn't cubic, maybe it was quadratic or something like, something like this. So maybe we call this first guy f of x, we call the second guy g of x. And my professor gets up there, he shades this portion of the graph. And he says, can you find this area? And one of my good friends, we weren't friends at the time, but we became fast friends after this, jumps up and says, yes. And the professor goes, great, do it. I'll give you an A right now, 100%. You get an A in this class if you can find this area. Because if you can find this area, you get the fuck out of pre-calc, for one. And my friend sits back down and he goes, well, I can't do it yet, but like, I know it can be done. Does that count? And the professor says no. We're going to learn how to do this, right? It's not anything too crazy. In fact, it makes more logical sense than a lot of the other things that we've tried to beat into our skulls this semester. And the trick, when things are relatively simple like this, is to picture the shaded area here as a difference of 2 areas. What I mean by that is, if you know the x value here, let me call it A, and you know the x value here, let me call it B, then I can find the area under this parabola, one little dash here, I can find the area under this parabola, or whatever that upper curve is, by integrating it from A to B. And I can find the area under the cubic the purple area here by integrating f from A to B. And then the pencil shaded area is just the blue area minus the purple area. That's the big idea, at least at the start. So the area I want is equal to the larger area, the blue area, minus the purple area. This works great. Well, so this is the thing I'm after, right? These two things I know how to calculate, and conveniently we can put them into a single integral. So the first guy would be the integral from a to b of the upper function here, which I've labeled as g of x. And the purple area would be the integral from a to b of f of x. And then following the rules for definite integrals, I know I can write this as the integral from a to b of g of x minus f of x, 1 dx here. That's pretty much the whole story for section 6.1. There's genuinely not a whole lot more to it than that. But there's a little bit more to it. Sometimes these areas are oriented sideways. Sometimes there's more than 2 curves or more than 2 intersection points. And we'll explore all of those subtleties more on Monday. But for today, I really just wanted to get us more practice calculating these integrals. We might wrap up a little bit early and expose you to the idea that the area between 2 curves can be thought of as a difference of areas, which can be thought of as a difference of integrals, which can be combined into a single integral. Most people remember this as the integral from a to b of the upper function minus the lower function dx. As a part of this, you need to find the intersection points. That can be kind of tricky. I mean, solving an algebra equation, but we know sometimes equation solving on its own can be a pain in the ass. So just finding the numbers a and b where these 2 curves touch can be a challenge. Sketching the graphs in the first place can be a challenge. So it's a neat section in that it kind of rolls together a bunch of skills from a lot of previous classes. But again, today I want to be focused on the integrals themselves. So let me pull up your text. And we can, is there anything relating to this here? Let's see. We looked at some fairly intimidating substitution problems last time. I don't think any of these are going to quite do what we're talking about here. Areas, substitution, and there are plenty of cool problems in here. Oh, 91 is good. We'll leave it here. I'm not going to beat that to death. So let's come into 6.1 and we can look for some problems here that allow us to invoke U sub. And we'll do lots more of these down the road. Oh, yeah, some of those are quite tricky. This. And sorry, just perusing. All right. Each one of 30 through 32 require a substitution. Now we can take a look at some of these. Let's start with number 30. We're going to sketch the region bounded between y equals x over the square root of 1 plus x squared, and y equals x over the square root of 9 minus x squared, where x is greater than or equal to 0. And then find the area. Neither of these are easy functions to graph. This first guy, we can play some games. So this first guy's domain is going to be all real numbers because 1 plus x squared is never negative, never 0. So this apparatus is defined everywhere. Upstairs, we have an x to the 1. Downstairs, we have an x to the 2, but it's under a radical. So I expect this to have a horizontal asymptote of 1 that it approaches on both sides, or perhaps -1 on the left. I don't think there's any shame in using a graphing utility. As with many of the homework problems, something like Desmos is just fine to take a look at the curves. I have it. So here's the first fellow. This guy's domain is going to be finite, right, from -3 to 3, because this downstairs is going to become negative outside of that interval and 0 at those endpoints. So they've asked us to sketch these curves and find the area bounded between them where x is greater than 0. So maybe if I call this f of x rather than y, call this phi of x rather than just x, then we can calculate this area. That's what we're looking for. So let's give ourselves a little sketch. The first curve is looking kind of like a logistic curve, if you've ever seen one of those. Or a little bit like the inverse tangent function, right, which we should be familiar with. That's the first guy. And the second guy, I mark this as like 3. The second guy is going to have vertical asymptotes at x equals plus and minus 3. We can take a quick peek back over here. And I'll draw him in red. He looks something like this. So this is y equals x over the square root of 9 minus x squared. And this is y equals x over the square root of 1 plus x squared. And the area I'm looking for here is this area. They said to only pay attention to the spot where x is greater than or equal to 0, so I'm not worried about the chunk on the left. I need to find the x value at this point. The one intersection point, the guy on the left, is clearly 0. But the intersection point on the right, that's not obvious. So we got to find those. We could cheat here and use Desmos again. But because this is a skill you're going to need to exhibit on the exam, I want to just walk you through the procedure. Equation solving can be work. So let's do it. Let's start at the beginning. If I want to find the point where two curves intersect, what do I do? algebra-wise.
Do you set them equal to each other?
Yeah, exactly, right? I'm trying to find the x value where this one function is equal to this other function. Those functions represent the y values. So I'm looking for a place where the y values are equal. That means I set this apparatus equal to this apparatus. As long as I'm free to assume that those denominators are non-zero, we can kind of cross multiply. We could also start out by squaring both sides. Both of those are valid options. I think maybe I'll start by cross multiplying and then square both sides. I'm going to need to get rid of those square roots. So if I multiply both sides by the square root of 1 plus x squared and the square root of 9 minus x squared, I'll get x times the square root of 9 minus x squared equals x times the square root of 1 plus x squared. And the step here was just to cross multiply. Then I can square both sides to get rid of the square roots. And this will become x squared times 9 minus x squared equals x squared times 1 plus x squared. When you square the x's, they become x squareds. When you square the square roots, the root vanishes, but nothing happens inside. Now this is an equality between polynomials. And we know how to solve polynomial equations. You blow everything apart, pull it all to one side, and try to factor. So we're going to do that. This is 9x squared minus x to the 4 equals x squared plus x to the 4. So fourth order polynomial equation. We'll pull everything to one side. And that will give me 0 equals x to the 4 plus x to the 4 is 2x to the 4. X squared minus 9x squared is minus 8x squared. I can factor out a 2x squared from everything. And what will be left here is just x squared minus 4. And the x squared minus 4, I can factor as a difference of squares. That's x minus 2 times x plus 2. So these two curves will smack into each other at 3 different x values. X equals 0, x equals 2, and x equals negative 2 from each of these factors, respectively. So the 0 we already knew. That's this fella. That means this must be x equals 2, and the guy over here that we don't actually care about because he's negative and we're not interested in that, we're just looking over here, that would be negative 2. So this is the setup, and there's plenty of work here. But if we're going to find that area, we got calculus to do. Any questions so far? Okay. So I've put all that information into my picture now by labeling those intersection points. We can come back and set up the integral. I'm going to cover up the left half there because I don't need that. I really just need the right half. that area between those two curves is going to be the integral from 0 to 2 of the upper function minus the lower function dx, which is the integral from 0 to 2 of my upper function in this region is the blue one, x over the square root of 1 plus x squared, minus my lower function here is the red one, that's x over the square root of 9 minus x squared dx. And for this particular problem, the way we'll handle this is by splitting it up, because each one of those requires a different substitution. They're both u sub, but each one requires a different u sub. So I'll handle this as the integral from 0 to 2 of x over root 1 plus x squared dx minus the integral from 0 to 2 of x over root 1 plus x squared dx. Pro tip, when you're doing more than one substitution, use different variables for the two substitutions. You don't want to confuse yourself by using u and u. So let me use something like u here is 1 plus x squared. I'm subbing for the inside of the radical. That's my inner function. And over here, I'll maybe substitute v equals 1 plus x squared. Oh, did I write? Shit. Goddamn. Should be a 9 minus x squared here. 9. 9 minus x squared here. Sorry. When I copied this down here, I just wrote the wrong denominator. This should be 9 minus x squared under the radical. So for each of them, we sub for the thing under the radical. We need our differentials. So if u is 1 plus x squared, then du is 2x. The derivative of 1 plus x squared is 0 plus 2x. So du is 2x dx. We're also going to need to change our bounds, so leave some space. And here, if v is 9 minus x squared, then dv is going to be minus 2x dx. And we'll need to change our bounds. When x is equal to 0 in the first integral, u is 1 plus 0 squared, which is 1. And when x is equal to 2 in the first integral, u is equal to 1 plus 2 squared. That's 1 plus 4 is 5. So there's all the stuff I need for my first substitution. I'll go ahead and set up the bounds for the second one as well. So the old bounds are 0 to 2. When x is equal to 0 in this integral, v would be equal to 9 minus 0 squared. So v would be equal to 9. And when x is equal to 2 in that integral, v would be 9 minus 2 squared is 9 minus 4 is 5. So there's everything for both substitutions. And that means that this is going to be integral from 1 to 5. The x dx here, I have an x dx here. So let me fill in the pieces that we see right away. Downstairs, I'm going to just have the square root of u. I think of this x as belonging to the dx here. So I'll just have a 1 upstairs. And then x dx is 1/2 of du. So take a second to make sure you see where the 1/2 is coming from and where the x went. This x dx is almost du. Du is 2x dx. So if you divide both sides of this relationship here by 2, or multiply by 1/2, you get 1/2 du is equal to x dx. So the x gets soaked up by du. We just have this factor of 1/2. Something similar is going to happen over here. So I'll write minus integral. The integral here is going to run from 9 to 5. So I know that seems like it's in the wrong order, but the lower bound 0 gets changed to the lower bound 9. The upper bound 2 gets changed to the upper bound 5. Put in the stuff we see right away. Downstairs, I have a square root of 9 minus x squared. That's going to be the square root of v. Upstairs, again, I have an x dx. And again, my differential has an x dx. So this x dx is going to get soaked up by dv. So I'm going to have just a 1 upstairs. This time, it's negative 1/2. Negative 1/2 dv, that is equal to x dx, dv. That is equal to x dx. Okay. So I think that's probably the step that is the most challenging, right? Is implementing and seeing how the substitution works. Are there any questions about where any of these pieces are coming from? We're all totally cool with the bounds being 1 to 5 and 9 to 5. Totally cool with the 1/2 and the negative 1/2. We can start playing some games. I can pop the positive 1/2 out of the first integral, and I'll be left with integral 1 to 5, 1 over the square root of u du. I can pop the negative 1/2 out of the second integral, and that's going to make that plus 1/2, integral 9 to 5, 1 over the square root of v dv. Like we talked about last time, I can flip these bounds over, and that will spit out a negative. You don't have to do it though. So here it's an extra step, it's an extra hassle. I might not bother doing that, and that's okay. I do, however, need to find an antiderivative. There's no getting away from that. So 1 over the square root of u, that's u to the negative 1/2 du. Maybe I will flip the bound. Since I have to take this extra step here, this plus is going to become a minus, and that will allow me to change this into the more appealing order from 5 to 9. And then 1 over root v, that's v to the negative 1/2. dv still chilling. Now we're ready for antiderivatives. If I add 1 to this power, negative 1/2 plus 1 is positive 1/2, so I'll have u to the positive 1/2. And I need to divide by that new power as well. Dividing by 1/2 is the same as multiplying by 2. And this piece gets evaluated from 1 to 5. And then I'll have minus 1/2, very similar stuff going on here. Add 1 to the power, you get v to the positive 1/2. Divide by 1/2 is the same as multiplying by 2. And we evaluate from 5 to 9. You can see that if you use the same variable, if you used u in both of these, at this stage, you could easily mislead yourself into believing you can put the two integrals together, right? Because you've got 1 to 5 and then 5 to 9, and it would look like u to the negative 1/2 and u to the negative 1/2. You could mistakenly believe that that's the same as the integral from 1 to 9 of u to the negative 1/2, but it's not. It's not, because different variables, they mean different things. Always wise to use different variables in your substitutions if you're doing more than one. The 1/2 and the 2 cancel in both instances. And from the first piece, we get 5 to the 1/2, or the square root of 5, minus 1 to the 1/2, or the square root of 1, minus. Second piece, we get 9 to the 1/2, the square root of 9, minus 5 to the 1/2, the square root of 5. If I take this up here and distribute the negative sign, of course, the square root of 1 is 1. I'll have a root 5 here, and then minus negative root 5. That's root 5 plus root 5, or 2 square roots of 5. The square root of 9 is 3, and the square root of 1 is 1, so I've got minus 1, minus 3. So let's annotate here a little bit. So negative 1 minus 3 is minus 4. And that's it. Pretty good stuff, right? Let me back out a little, and here's the whole integration process. Questions on the substitutions? Questions on why we yield these integrals? Questions from here on? Okay, let's try another then. There are some other fun ones here. We've got this fella and this fella. And they both look cool. We got all the time in the world. Let's do 31. X over 1 plus x squared. I actually know what that graph looks like. Let me write this down. The first guy I know, the second one I don't. All right, so don't feel bad if these aren't jumping out at you right away. And I will go ahead and look at these in Desmos before I draw them, because even though we know this is like a serpentine thing, it's like, let's see, this negative over here goes cool S-curve shape. I want to get the relative scales correct. So Okay. Yeah, so the black curve is not one that I know, and he is definitely more complicated. The purple curve here is one that we know pretty well. That's a pretty standard serpentine curve. And it looks like the area we're going to be hunting for is this area. So let me try to sketch the black curve first. Rather than doing it in black, I'm going to do this in blue. We do have a vertical asymptote there at -1. That makes sense, because that denominator is undefined, is equal to 0 when x is -1. Looks like we have a max somewhere just to the right of +1. Let's do our best. So something like this going on over here. And then we tag +1 over here, so I have a reference point. Say my max is up here. And yeah, we go through the origin, right? Okay. So I'll do in purple. Something like that. Oh shit, no, this is all supposed to be in blue. Damn, 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 damn. Same curve, sorry. Here I was all proud of drawing a nice pretty picture. Yeah, I'll run back over this in purple. No, not really. They don't blend, do they? Close enough. All right. So here is the weirder curve, y equals x squared over 1 plus x cubed. And then that serpentine curve, we'll do him in red. Where's his min and max? I think they're at plus and minus 1. Yeah. Okay. Let's say something like this. Yep, good enough. All right. So we have to look for a spot where this is actually bounding a closed region. There are a couple of regions here we could look at where there is area between the two curves. Here, and even over here. But the only place where I have a closed bounded region is from here to here. So the area I'm after is this. Which means my red curve is going to be my upper curve. And my bluish curve is going to be my lower curve. I think I may wish I could have shifted this around a little bit, but it's going to be just fine. So I need to find the intersection points. Sometimes when mathematicians just want to pull things out of their ass, they say by inspection, the following is true, meaning stare at it until you see it. I won't do that to you here, but you could stare at these long enough and realize that if x is equal to 1, they're going to be equal to each other, right? The top would be 1, the bottom would be 2, top would be 1, bottom would be 2. But if we didn't see that, we would set them equal. and cross our fingers that we can handle the resulting equation. Again, cross multiplication gets us started. So this will be x times 1 plus x cubed equals x squared times 1 plus x squared, which is the same as x plus x to the 4 equals x squared plus x to the 4. And if I pull everything to one side, x to the 4 minus x to the 4 is 0. That's nice. And then x squared minus x is all that's left. And this, if I factor out an x, I get x times x minus 1. So yeah, this max should be at this intersection point. That's okay. Retcon that shit a little bit, and we'll label this point as x equals 1. Good enough. So then I'm looking for the area between the red and blue curves from 0 to 1, which means I'll be integrating the upper minus the lower. From 0 to 1. That will be integral 0 to 1, x over 1 plus x squared minus x squared over 1 plus x cubed dx. And like the previous one, these are each going to require a different substitution. So I'm going to split this up as integral x over 1 plus x squared dx minus integral 0 to 1 x squared over 1 plus x cubed dx. And maybe for fun, I'll use like w and z here for my substitution variables. So in the first one, what would I substitute? I'm going to use w. What would I substitute for w in the first integral?
X.
So substituting like u equals x or w equals x only ever has the effect of like changing all the variables to w. So it wouldn't, I would get w over 1 plus w squared dw, and it would still run from 0 to 1. So while that's a valid substitution, it's not necessarily a helpful one. When I look at this guy, kind of the thing that's making life hard is the denominator. And if I look at the derivative of that denominator, it's almost exactly the numerator, right? 2x, just an x here. So I'm going to sub for the bottom, w equals 1 plus x squared. Kind of thinking of this as like a 1 over w. Because then dw is 2x dx. So that's going to take this x dx and soak it up. And x is equal to 0, w is going to be equal to 1, right? 1 plus 0 squared. When x is equal to 1, w is going to be equal to 2, 1 plus 1 squared. So that's the substitution in the first integral. I'll use the letter z to substitute in the second integral. And the same sort of ethos works here, right? I think of this as like a 1 over z. and the x squared dx is almost exactly dz because the derivative of 1 plus x cubed is 3x squared. So sub z equals 1 plus x cubed. And then dz is going to be 3x squared dx. And the work for the bounds here is almost identical. When we plug in 0 for x, the z is going to be 1 plus 0 cubed, which is 1. When I plug in 1 for x, z is going to be 1 plus 1 cubed, which is 2. So these are the two substitutions.
So since they turned out the same, can we just combine it like it was?
It's tempting, but remember z and w represent different things. In some instances, we might be able to because they are dummy variables. But let's see what we get. And then we can talk about whether they can or cannot be combined. So we're going to have the integral from 1 to 2. And this first guy is going to go from 1 to 2. X dx is 1/2 dw, and 1 over x, 1 plus x squared is going to be 1 over w. So this is 1 over w times 1/2 dw, and then minus integral 1 to 2. X squared dx is going to be 1/3 dz, right? And then the 1 over 1 plus x cubed is going to be 1 over z. So I have 1 over z times 1/3 dz. It is true in this case because the bounds match, and we're talking about definite integrals, that if you had used the same letter for your two substitutions and then chose to recombine this into a single integral, you could. You could. That would fly here. But in general, it does not fly. So my advice is to not get into that habit. So I will handle these separately, although you could relabel one of these with the other's variable, like call this 1 over w, 1/3 dw, and then put them together. You could, but it doesn't save you a lot of time. And what's worse is there are so many more situations where you can't do that, that I would advise just handling them separately. So this is 1/2 integral 1 to 2, 1 over w dw, minus 1/3 integral 1 to 2, 1 over z dz. And each one of those will give you a natural log. This is going to be 1/2 natural log absolute value of w evaluated from 1 to 2 minus 1/3 ln absolute z from 1 to 2. So that first guy, when you plug in 2, you're going to get the natural log of the absolute value of 2. The absolute value of 2 is just 2. And we subtract what we get when we plug in the lower bound. Same sort of thing, the absolute value of 1 is 1. So the absolute values go away there. And then minus 1/3, exactly the same sort of shit here. Natural log absolute value of 2 is 2. Minus natural log absolute value of 1 is 1. Ln of 1 is 0. So those go away. And we just get 1/2 natural log of 2 minus 1/3 natural log of 2. And 1/2 minus 1/3 is 1/6. So this is 1/6 natural log of 2. And it is true if you combined these, right? If you did use the same variable, say z in both, and you combine these, you would get a 1/6 integral from 1 to 2, 1 over z dz. It would get you there a tiny bit faster. It would get you there a tiny bit faster. This is how I would do it. Right? Even if I was doing it myself for my own reasons, not just trying to like stay away from possibly confusing things because I'm teaching a class. Even if I was doing this for my own reasons, this is how I would do it. I would not combine these. It's a teensy bit more writing, but I think it's worthwhile to have a really legible workflow. Questions on any of the integration work here?
We technically don't have to draw the graph, right? You can just do all this with just the equations.
Well, you got to know which function is the upper function and which function is the lower function. So if for no other reason than that, it's worthwhile to draw the graph. And if you want to get more kind of granular, like class logic, there may well be a problem on the exam where I ask you to sketch a graph and then shade the area and then find the area. Now, if I did that to you, would I give you something this complicated? Probably not. Could we? Yes. Right? Can we absolutely use the methods from the end of chapter 4 to sketch these two curves beautifully? Yes, we can. We can calculate all of the intercepts, asymptotes, increasing, decreasing mins, maxes, inflection points, blah, 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 for both of these and draw beautiful graphs for both 100% from by hand using the techniques that we learned earlier in the term. Would I expect you to do that for a problem like this on the test? No. I would give you something whose graph you should know, right? Something that is in your set of parent functions. Remember, if you look in the modules, there is a set of graphs that you are responsible for. By the way, if you want to review how to graph those specific functions the lazy way without any calculus, you can get really good results just following this stuff. You won't get the mins or maxes right, but that's okay. But the sort of stuff that I would expect you to be able to play that game with by hand on a test, in a test setting, would be coming from this Desmos link here. This is going to look busy as all hell. I don't know. So certainly any one of these, I would expect you to be able to produce for me. Oh, that's the old one. Yeah, including sines, cosines, exponentials. And the bother them. So, real quick, save and replace this. So the sort of things I might ask you to, oh no, that one says that's supposed to be MAC 11. God damn it. I don't have these that's all I funny. And read the whole thing. Anyway, this would be the stuff that I would hold you responsible for on a test. We've got time for one more, and the integrals in that last one are kind of fun. Now, if we want to try to approach this without drawing the graphs, we can, and I can show you a trick or two. Natural log of x over x, natural log of x all squared over x, and we want to do the same thing, find the area bounded. Again, neither of these are curves that I know right off the top of my head. And if I wanted to sketch the graph by hand, I would have to go through that big procedure from section 4.7 or 4.5, whatever that was. But we can try to do as much of this as possible without drawing the graph. We can start by saying I'm going to find the intersection points. By setting these equal. And this time, when I cross multiply to get rid of those denominators, I'm going to get x ln x equals x ln x squared, like this. And then I can divide through and cancel the x's as long as I know that they're non-zero. And it is implied that x is non-zero here because the natural log function cannot take 0 as an input. So you're going to cancel a factor side to side. You need to make note of where that factor is 0. It can produce holes in the graph, or you can lose solutions to this equation. But x equals 0 couldn't possibly be a solution to this equation because these things are both undefined at 0. Does anybody remember how to solve equations like this? So this is not a polynomial, but I can kind of think of it as a polynomial whose variable, rather than being x, is the natural log of x. Sometimes people say they're going to make a substitution algebraically. I'll just write it like this. I'll subtract the natural log of x from both sides. And then I'll factor out a natural log of x. Should give me natural log of x times the natural log of x minus 1. Totally valid, right? And if you want to, you can think of this as like u squared minus u, right? And of course, you can factor a u there and you get u times u minus 1, same bullshit. So now I can set the natural log of x equal to 0. And here I would get ln of x minus 1 equals 0. How do you solve this equation? I just put my college algebra students through absolute hell with this stuff, so I'm excited to see kind of where we're at. In general, to solve logarithmic equations, you exponentiate on both sides. You isolate the log term and then exponentiate using whatever base the logarithm is. So the natural log is a base e logarithm, so I would exponentiate on both sides base e. On the left-hand side, e to the natural log of x is just x. On the right-hand side, e to the 0 is 1. So x equals 1 is an intersection point for these curves. This other guy, I'll do the same sort of thing. I'll add the 1 over and then exponentiate. And then again, e to the natural log of x is just x. E to the 1 is e. So the intersection points occur at x equals 1 and at x equals e. But the question is, who is the upper and who is the lower? Can anybody suggest a way to test? So between 1 and E, let me just draw on some bullshit graph here. If we plug in 1, then this is going to be 0 over 1, which is 0, and so will the other guys. So they intersect here at the point 1 comma 0. If I plug in E, then this is going to be 1 over E. So the intersection point there has y value 1 over E. Something like this. And between those, 1 is always above the other, right? Because the only way for them to trade places would be to cross, which would mean we have another intersection point, but these are the only two. One way to get the answer to the question, who's above who, is to test a point. Plug some x value from this interval into both and see which one is larger. And then you can tell who's the upper and who's the lower without the graph. Now, a number between 1 and E that is also nice to plug into a natural logarithm. Can anybody suggest one of those? Now, you know, E is like 2.7, right? So you could always test 2, right? That would fly. But the natural log of 2 is not a number that probably most of us know very well, right? It's like 0.69. You can remember that because 69, nice. But it's not the easiest thing in the world. I would recommend using a power of E. Those are the numbers that are nice to plug into logarithms. So if I need a power of E that is between E to the 0 and E to the 1, I could use like E to the 1/2. So the first curve, if I plug E to the 1/2 in, upstairs I get the natural log of E to the 1/2, which is 1/2. Downstairs I have E to the 1/2. This is 1 over 2 times the square root of E. Let me call these like y1, y1, and y2. Here's y1. And if I plug that same x value into y2, I get the natural log of E to the 1/2 all squared divided by E to the 1/2. And again, the natural log of E to the 1/2 is just going to be 1/2. So this numerator is 1/2 squared over E to the 1/2. So that's 1/4 over E to the 1/2, or 1 over 4 square roots of E. So who's bigger, y1 or y2?
One.
Good, y1 is larger. This is 2 times larger than this. So y1 is my upper. And y2 is my lower. Now, that's a reasonable amount of work in itself, right? I know what most people would do. Most people would look on WebAssign and be like, click the graph until you get the right one and then go, okay. Prior to the epoch of WebAssign homework, most people would put this shit in a graphing calculator, right? And that's okay. This, however, is an approach that will work on a desert island or on an exam. If you're not cheating and you need to know, then this will do it. Again, on an exam, I'll give you curves that you recognize. So now we're ready to set up the integral. Y1 is the upper, Y2 is the lower. My intersection points are 1 and E. So I'll be integrating from 1 to E, Y1, you can't see that, can you? Y1 minus Y2. That's the natural log of X over X minus natural log of X squared over X. Yes. Now, the reason I was excited to get to this problem is because here is an example where we can do everything all at once. Calculating an antiderivative for either of those requires the same substitution. So I'm going to go ahead, we've already got a common denominator here. I can write this as the natural log of X minus the natural log of X all squared divided by X dx. And I'm going to do one more little bit of algebra before we push the substitution in. All right, this is integral 1 to E, natural log of X minus natural log of X all squared times 1 over X dx. And I think this will help you with the substitution. So what is that substitution?
lnx.
Yeah. So I'll make the sub z equals the natural log of X. The reason I wrote this out here is because I thought it might help us spot that, because then dz is 1 over x dx. Right, so 1 over x dx, that's our guy. And this will just become z minus c squared. Got to change those bounds. Anytime we make a substitution in a definite interval, we've got to change the bounds. So my old bounds were x equals 1 to x equals e. When x is 1, z is the natural log of 1, which is 0. When x is e, z is the natural log of e, which is 1. So this is going to become the integral from 0 to 1 of ln x, that's z, minus ln of x all squared is z squared. And this couldn't be more beautiful. 1 over x dx is exactly dz. The power rule will handle everything from here. Z itself integrates to 1/2 z squared. Minus is this minus. Z squared integrates to 1/3 z cubed. And we need to evaluate from 0 to 1. At the upper bound, I'm plugging in 1 for z, I'm just going to get 1/2 minus 1/3. At the lower bound, I'm going to get 0 minus 0. there's that difference of 1/2 and 1/3 again. That's just 1/6. So that is the game. The last thing I'd like to do before we leave is just to take a look at this graph because it's a mystery to us still. Let's see how we did. Any questions about the integration steps here? Any of the algebra that we did with the integrand? Why we did it? Anything like that? If you want to, you could have split this up and done each one separately. Here I took care of it with one integral and one substitution because it's the same substitution in both. All right, let's take a peek at the graph. Not bad, right? The intersection points are what we thought. 2.718, that's E. As we suspected. So the area we found here was this area. All right, in parting, I'm going to leave you with one last tiny idea. Natural logarithms in general, are the bane of algebra students' lives. Right? I've been seeing this and feeling it pretty intensely lately because my college algebra students are just now being held responsible for what they're supposed to have learned about logarithms through the term. You learned, no doubt, that the base b log of x is defined as the inverse to the function b to the x. And that's fine. There's nothing wrong with that. So in particular, that the natural log is the inverse of the natural exponential. And this is what you take as the definition of the logarithm in algebra classes, because they're algebra classes. But logarithms' native territory is not algebra, it's calculus. They are inherently calculus objects. So are exponential functions. And the better definition is to define the natural log of x as the integral from 1 to x of 1 over t dt. And if you evaluate this integral, if you calculate this thing, you're going to get ln of x because your antiderivative for 1 over t is ln absolute value t. And then you plug in the bound, so you get ln x minus ln 1, which is just ln x. Yay! See if you can deduce any properties of ln x from this definition. And remember, the properties we're talking about there are things like ln of x times y is ln of x plus ln of y. Ln of x over y is ln of x minus ln of y, and ln of x to the y is y times the natural log of x. It's a really fun exercise. It's something that in an honors class I assign as a little project. It's not super straightforward. It's going to take some work and some thought, and it's definitely not something I would test you on. But if you want to stretch your skills and kind of practice getting really good with properties of integrals, right? Because if we define this function to be an integral, then you can most certainly cook up these results. But it's going to take some work. It's going to take a little bit of work. So I invite you to play with that. It's a lot of fun. And with that, I will go ahead and wrap things up here. Are there any burning questions? Anything you guys would like to ask before we conclude for the day? Alrighty, practice your U sub. Make sure you're getting good at that stuff. If you want more fun problems to work with related to U sub, there's a lot of stuff in section 5.5 of the textbook that does not translate into web assignable things. So like all of your homework questions come from 1 through 73, but the later questions in this section are dope. They're really, really good. So see if you can solve some of these also. If you want more practice, you want to get good at U sub, see what you can do with some of these later questions, especially these guys like 87 through 94. These are all awesome, awesome problems. And with that, I will conclude here. The study guide is up. I posted that on Wednesday after class. If you're looking for other extra practice, remember the reviews at the end of the chapters in the textbook are really good. So lots of questions about integrals. Which one of these things are true? I'll give you a hint. They're definitely not all true. Like this is mad bullshit. This is mad bullshit. But see if you can figure it out for yourself and really convince yourself. And then the review exercises are also very, very good. All right, I'll go ahead and end it here. I hope you guys have a lovely rest of your day, and I will see you on Monday. Remember, our exam is next Wednesday, right? We opted to do it on Wednesday, so we have Friday to review for the final. So get ready for test 3, work on that study guide. Sooner you get that in, the better I have a chance of getting you some feedback before the test. If you need anything, office hours, you know the drill. See you guys later.